Okay, let's do it. So this 3.4 has some intimidating language in the title, right? We have inverse functions, which we just started learning about in the last class, and then we have trig, which is always pleasant, right? And putting them together. So now we're going to be talking about inverse trig functions, but it's not too bad. Make sure you're asking questions or asking for clarification if you feel like you're not understanding something. So remember what we said, for a function to have an inverse, it has to be one-to-one. Thus, it has to pass the horizontal line test. Trig functions, all three of our main trig functions, sine, cosine, and tangent, and in fact all of the trig functions, even the reciprocal ones, are what we call periodic, meaning they repeat over and over again, infinitely. Meaning none of them pass that horizontal line test, right? In fact, they fail it as pretty much as badly as you can fail the horizontal line test. So how could we possibly talk about inverses of trig functions if it fails the horizontal line test? Well, the other characteristic of trig functions is that they repeat their behavior. It's not like they do something interesting and new. They just continue to repeat whatever their behavior is. So sine and cosine are wave functions, so they just are a wave that keeps repeating. Tangent, right, is an asymptotic function, but it just repeats its asymptotic behavior over and over again periodically. So what I can do then is choose to restrict the domain of these functions so that I'm only looking at a piece of them, and I can restrict it in such a way that the piece I'm looking at does pass the horizontal line test. Now, we could do that in many different places since they repeat the same behavior over and over again. What we choose to do is we tend to restrict the domain pretty close to the origin, just for ease of use. You could do it literally an infinite number of places. So for sine, we're going to go, okay, let's restrict this domain. And we want to restrict it in a way so that the sine function still hits all the possible y values that it's ever going to hit, but it only does it once, and it doesn't repeat. So if I just look at that piece, does that single piece pass the horizontal line test? Right? The answer is yes, it will. There's nowhere that I'll be able to draw a horizontal line that will hit more than once. All right, and that piece also represents all the possible y values that sine will ever attain. So if I choose to look at sine only on the domain from here to here, which is negative pi over 2 to pi over 2, then sine does pass the horizontal line test. It is one-to-one, and then it will make sense to talk about the inverse function of sine. Sine should have an inverse in that case, if that makes sense. All right. So we restrict the domain between negative and positive pi over 2. That gives us just that piece. And then it makes sense to talk about the inverse sine function. The inverse sine function is just y equals, this is the notation for it, inverse sine x. Or you can write y equals arc sine x. Those mean the same thing. Okay? So inverse sine means the same thing as arc sine. All right, and here's the definition, right? If inverse sine of x equals y, that means sine of y equals x. So it would have an inverse relationship. It would swap the input and the output of the original function. Go ahead and write what's in the blue box, then give me a green check when you're ready to move on. All right, so it's important to remember that inverse functions undo each other. So if I compose inverse sine and regular sine, they cancel each other out and I'm left with x. If I compose sine and inverse sine. They also cancel each other out, and I'm left with x. All right, we're going to move forward here. So let's do an example. We'll just talk about evaluating inverse sine. So if I'm looking for example, arc sine of 1/2, or inverse sine of 1/2, I know that's going to equal some value. Let's call it x, right? Well, I could take sine on both sides. So I'll have sine of the left-hand side, sine of the right-hand side. These will cancel each other out. Really what it's saying is, okay, sine of x equals 1/2. So I'm looking for the angle x such that that angle, when I take sine of that angle, it gives us an output of 1/2. Now that angle has to come from the restricted domain. So that angle is going to be some value between negative pi over 2 and positive pi over 2. Okay? All right. Well, negative pi over 2 and positive pi over 2. That's either this quadrant, right? Or this quadrant. Because this is pi over 2 up here. This is negative pi over 2 down here. All right. The other thing is this. I told you that when you're going to do things by hand, you only need to know two special triangles, a 30, 60, 90 triangle and a 45, 45, 90 triangle. Which one of those can possibly produce a ratio of 1/2? 30, 60, 90 or 45, 45, 90? So I'll remind you about the ratios. 30, 60, 90, we have 1, 2, rad 3. 45, 45, 90, we have 1, 1, rad 2. So 45, 45, 90, you could get 1 over rad 2, but you can't just get 1 over 2. 30, 60, 90, you can get a ratio of 1 over 2. Now, which angle, 30 or 60, is sine of that angle 1/2? Think about your geometry definition of your trig function. Sine is opposite over hypotenuse. So which angle does sine produce that ratio of 1/2 for you? Good. I agree, 30. So if we're looking from the perspective of the 30, the opposite is 1, the hypotenuse is 2. So my reference angle is 30. Now, we know it has to be either in this quadrant, quadrant 2, or quadrant 3, right? You know what? I think I just forgot the way the quadrants are labeled, guys. Do they go, oh boy, I feel embarrassed. I'm going to be in, because we need it to be positive 1/2. So our reference angle is 30. So it can either be that or that. But for this one, notice that the y component is below the x-axis. So we would actually, this will be labeled -2, right? So it'd be negative 1/2. So it has to be the one in the first quadrant. It has to be this angle. right? All right. So what does that angle correspond to in radians? Well, 30 times pi over 180 is pi over 6. Okay. So our final answer is that x equals pi over 6 for that first one. All right, so let's do the second one. The second one is tangent of arcsine of 1/3. Here's what you have to remember. For a regular trig function, you input an angle. So you do sine of some sort of an angle. And you get an output that is a ratio or a value, right? So sine is always opposite over adjacent, or sorry, opposite over hypotenuse. Now, when we take inverse sine, it switches that, right? So when I'm thinking about inverse sine or arcsine, I input a ratio and my output is an angle. And so here's what I want you to think about for this next one. We have a composite function. We're not asked to do any calculus. We're just trying to evaluate it. And so what we have is tangent of arcsine of 1/3. If I just look at the arcsine of 1/3, what type of output do I get? Do I get a ratio output or an angle output in the chat? It's going to be an angle, right? So what I'm going to think about is, let's call it theta, because we oftentimes use Greek letters for angles. So I know that arcsine of 1/3 equals theta, right? So let's take sine of both sides again. What's sine of arcsine of 1/3? What is this left-hand side here going to simplify to? What happens when you compose two functions? Yeah, they're just two inverse functions. They're going to cancel each other out. I'm just left with 1/3 equals sine of theta. We can set up a triangle to represent that scenario. Draw yourself a right triangle. Put theta as one of the acute angles. Now we know that sine is opposite over hypotenuse. So since sine is 1/3, the opposite side is 1. The hypotenuse is 3. I can think of this as b. And then there's a relationship between those sides in a right triangle, right? Probably the most famous geometry formula, which is Pythagorean theorem. And we have that b squared, or I should say 1 squared plus b squared equals 3 squared. So b squared then equals 9 minus 1. B squared equals 8. So b is the square root of 8, right? So here's the thing. Up here, we decided to call arcsine of 1/3 theta, right? So it's fair to say that really what I'm looking for here is tangent of theta. And now I can find tangent of theta without actually having to evaluate arcsine of 1/3, because I built a triangle that involves theta. So in the chat, what would tangent of theta in that triangle be? What ratio in a triangle is tangent? Remember SOHCAHTOA, tangent is opposite over hypotenuse. So in our triangle that involves theta, the opposite of theta is 1. The hypotenuse is rad 8. So it's true that tangent is 1 over rad 8. And so we were able to evaluate tangent of arcsine of 1/3 by building a triangle that satisfied arcsine of 1/3, finding the third side, and then just using that triangle to evaluate tangent of theta. Okay. So we already made this statement that the inverse function, when you compose two inverse functions, they're going to cancel each other out. I'm going to jump over that. So this is the graph of inverse sine. Remember, it's just the reflection of the graph of sine on that same interval reflected over the line y equals x. So it's just the reflection of the graph of sine over that line. We know the sine function is continuous, so inverse is also continuous. And the sine function is differentiable, so inverse sine should also be differentiable. What I want to do right now is just go over how we find the derivative of inverse sine. We're going to derive these formulas for all three trig functions. And it's not too bad, but it does involve some implicit differentiation. So here's what I want. I'm going to say that y equals inverse sine of x. Okay? What I want to figure out then is what y prime is. That's my goal. All right. Well, one thing I can do is, once again, I'm going to take sine on both sides of this function, both sides of this equal sign. So I'm going to take sine of y, and I'm going to do the same thing over here. I'm going to take sine of inverse sine of x. All right. Now on the right-hand side, what is this going to simplify to? What happens when I compose those two functions? So sine of inverse sine of x is just going to leave me with what? With just x, right? I agree. So what I have now, after simplifying, is that sine of y equals x. Okay. So one thing I want to do right now is that in this scenario, y would be considered an angle, right? Because our input for regular trig functions is angles, and our output is a ratio of sides of a triangle on those angles, right? And I can rewrite x as x over 1, just so it's a ratio, okay? So if I built a triangle out of that, here's a right triangle, it would be true that this would be angle y. And then remember, the ratio for sine is opposite over hypotenuse. So the opposite of angle y would be x, and the hypotenuse would be 1, right? Okay. Well, I could then come up with an expression for the third side of that triangle by using the Pythagorean relationship. Let's say I call that side b. Do you agree that x squared plus b squared has to equal the hypotenuse squared? Because it's a right triangle, right? So let's just solve for b. So then I would say b squared equals 1 minus x squared. And then we would just take a square root on both sides. and it's true that b is equal to the square root of 1 minus x squared. So an expression that could represent the third side of the triangle is rad 1 minus x squared. Okay, so we're going to be using that triangle in a moment, but I'm going to just go back to the equation that we have where sine y equals x. Now, I want to remind you what we're looking for is y prime. All right, so I'm going to use implicit differentiation here. I'm going to rewrite sine y as sine of f of x equals x. And then I'm going to take the derivative on both sides with respect to x. So this is just implicit differentiation. All right, to take the derivative of that left-hand side, I'm going to have to use the chain rule, right? So the derivative of the outside function is just cosine, leave the inside, times the derivative of the inside function, so times f prime, right? The derivative of the right-hand side is just 1. All right, so we've gone and taken the derivative of both sides. Let's put this back in terms of y. So we have cosine y times y prime equals 1. Again, the thing we're looking for is y prime. So I'm just going to isolate y prime by dividing out the cosine y. So y prime equals 1 over cosine y, which is the true derivative, but since my original function wasn't implicitly defined, my original function was just given as y as a function of x, I would like my derivative to also just be a function of x. And that's where our triangle comes in. 1 over cosine y. Cosine is adjacent over hypotenuse, right? Well, the adjacent to y is just the rad 1 minus x squared. So I have y prime equals 1 over rad 1 minus x squared. Because adjacent over hypotenuse would just still give me root 1 minus x squared over 1, which is just root 1 minus x squared. So there, I found that my derivative of inverse sine is 1 over 1 minus x squared. Derivative of inverse sine is just 1 over rad 1 minus x squared. Okay. I'm going to stop there for today.